So, ladies and gentlemen, welcome back. I hope you had a pleasant break. So please join me to welcome Dr. Steevy Cordette. He's the Director of Advanced Photonic Research Department, as well as he's the Director of Energy Research Center at the TII. For a very interesting talk, he will tell us more about advancing the quantum frontiers from photonic point of view. Please come.
Hi, thank you for the introduction. Okay, laser. Seems that the laser doesn't work. We're going to talk about photonics, so it will be good to have some laser. Okay, anyway. So today my talk will be on how integrated photonics could help on the advance of the quantum technology. Currently there is many platforms for quantum technologies, and up to now the photonics was not seen as a flagship for the implementation of this technology. I mean, of course, since the beginning of the history, photonics was the platform to show some theoretical proof, concept, and so in the lab. But it was still seen as a big issue to go for the scalability in order to have the enough number of bits to have, for example, the supremacy or the advantage that could come from the quantum technology. This was before, because now we know that it could be achieved with some demonstration in the lab on the tabletop has been done, showing that we could have the quantum advantage at least, but with a quite complex setup. And without having the way to, let's say, having the programming, the way to reconfigure the system in an easy way. So it was still not, it was still not at the level of readiness to compete with the other technology, where you start to have the way to at least address key criteria that is needed for the use of the quantum technology. But we know that anyway, photons is a good platform for other means, because at the end it's working at room temperature. We have the way, this is a good carrier as a fly qubit, in order to have it transfer the information, the quantum information, from a point A to a point B. And this is why looking at the way to at least having a better integration, easy way to have the full system in a small footprint, and as well the way to be able to have the reconfiguration of the system is important. Focusing on the integrating photonics. So this is a technology which has been derived massively by the telecom industry in order to have easy way to play with the property of the light, to encode classical information, and to able to have the communication system that we are all using, basically the fiber-based communication, and more now on as well the free space optics communication. And to do this, in order to have the number of transmitters that is needed to have the full network, so a massive train in order to address this kind of technology was needed. So there is different platform with the common pros let's say we could have the category to say some is better for passive with low loss, some is better for active to play with actively with the light, and we have some structure which are there, but that allow to do splitting, to modulate the light, to have as well the way to go in the chip, because it's not always easy. We need specific building block for that. But having all those platforms is challenging, but the industry is pushing to have more and more, at least hybrid integration, having each feature on each different chips, and even more, going more and more for a full integration on the same dies. Now, the question is how this technology, which is available, which is start to be at the good maturation, could be transferred to be used for the quantum technology. If you're looking here at the scheme, we know that at least the first step is to be able to do the basic operation, and then to have the way to address the different criteria on the chip for the criteria for the deficiency criteria. And to do this is not an easy path, and this is why it was so challenging to achieve this shift here, this paradigm shift here that you could see. You see the work, how you have this kind of takeoff of this technology for that application. And to do this, it's important to understand the way to, let's say, leverage on the photon to do that, and to understand what we need to address as a challenge. So we need to have the way to have a good quality control of the qubit, to have the way to have the good quality of the qubit itself, and even more, having the way to have scalability, as I was mentioning before, high level of integration. And thanks to that, we will start to migrate from the classic optics with this technology to more quantum technology and even more. Currently, if you're looking at the quantum technology, it wants the way we could have to address the operation for the gate. There is two framework. The first one is to use the discrete form. I mean the discrete which is based on the qubit itself, to say that you have two values, 1 and 0. But once you start to have many qubits, it starts to be challenging, because at the end you will have an additional noise that will come, because you will need to have those qubits together with good quality, as I was mentioning, so without interferencing between them. And for this, you have the typical gate that you could see at the bottom here, the Adammer, the Keynote, and so, which is based on interferencing with Mach-Zehnder interferometer that could be tunable, by the way, if you go to the chip in an easy way. And you have the other framework, which is based on the Q mode. Here we no more talk about qubit, but Q mode. The Q mode is to say that at the end, you will start to looking at not only one level, but many level, as you could see here, many Q mode that will allow you to have still good orthogonality, let's say, between the different Q, between the different sub-level of these Q modes. And the good thing is that for that, we could also address better the way we could use the current technology. So, looking at the way that we have this, let's say, robustness of the system, we see that actually we need to control well the loss, and we need as well to control well the phase which is induced by the system. And for this, as well, the community is already working out on the way to address the way to go for low loss. We need as well to have the way to have non-linearities to control the way we could generate over frequency in order to have the generation of as well a single photon on the chip. And we have some proof of concept already proved in the community. But what is important for the Q mode is the squeezing as well function. To do that, it's important to consider the non-linearity of the system. So having this kind of feature is important. And you see as well that at the end what's counts is not just the non-linearity, but the ratio between non-linearities and loss. And you see here from this picture how it's important to have the both, like the best word will be to have high non-linearity and low loss. Some platform is really interesting for this purpose. We have, for example, the lithium niobate, which is a platform that allows to have a good control of the light, as well as a good integration of it. So based on that, we could address those needs in order to have feature has OPA that allow to have the second harmonic generation, to have as well the spontaneous down conversion on the same platform with good efficiency. As well, we need to have a detector that address the need of single photon detection. And those technology is already based on the silicon for many of them. Another good interesting part is to look at the way to get high density of element, because the higher density you will have, the less loss per element you will also achieve. And so it's again a question about how many loss I could support in my full system. So you could use 3D printing as well to have this kind of higher density, which is interesting. And by the way, some simulation has been already done to show how much you have fidelity using gate based on this kind of technology. The same here for this, for the, let's say, once you're looking at the full system of the quantum computer, for example, and you see how much the fidelity based on the chip system is interesting. Because we could reach close to the same level of fidelity as the current system, which is about 96% of fidelity, even 99 for some. So here is already some key milestone happening in what was already proved for this kind of platform. There is different platform of photonics for that, but what is interesting is that we could already talk about application, even very large scale, because some proof of concept has been already done also for large scale using full wafer that allow also to have bigger number of elements in the system. And so once you go back to the demonstration done by Zhu Hang number 2, you see that even them, they start to look at for the version 3 integrating peak system, not for the full system, but at least for the part for the interferometer based on the Mach-Zehnder network that you could see here in blue. Once you look at the application, here I will show some application where we have used, where it has been used peak technology for quantum technology. Basically, you have already in the market some chip that allow to do this scheme using the Mach-Zehnder interferometer in order to use the linear optics as quantum for quantum processing with a good fidelity. Test for some calculation for vibration of some material in order to compare with the classical computing. There is even many players Here is another player, which is Candela, working as well with the same technology, but with having the benefit of quantum dot as a seed for the system, and showing good performances compared to other technologies. You have to focus. If you want to focus on something, you could focus on the fidelity that show very good results in terms of fidelity in percentage. I mean, 99%. It's quite good compared to the other technology. And we have also cryptography. This is a good example where it has been used a peak system in order to have this cryptography communication between Alice and Bob. I try to go fast because I don't have so much time. And you have as well the integrated photonics, which is help for the 3D magneto-optical trap. So here what is going on is that you have some antenna, and those antenna is crossing together in space in order to have the way to stabilize some particle in the air. I think my time is more than up, so thank you very much for your attention. I would say as a last word that here we did not use all the degree of freedom of the photon. Mainly what was used more the special one, using many paths. But we have many other kind of way to encode the quantum information using over multiplexing technique, which is time, which is shown in the presentation as well, but frequency, and even looking at some specific beam shape. Thank you very much.